So here are the results of the transient analysis. You can see we dropped the water table a little bit, so we get a little bit of reduction in pressure. It's not that easy to see here, but we can click on the previous state just to compare. So if I click on slope GW2, you can see that the pressure contours are a little bit higher than they are in this transient analysis. The water table dropped a little bit, but it's not super noticeable. Remember that the water table is the boundary between saturated and desaturated. It doesn't necessarily correspond exactly to where we set the head at the right-hand boundary here. The pore pressures for the transient, we can see the effect of dropping the water table on the right-hand side. We can also see the effect on the displacements. So dropping the water table caused a little bit of downward displacement. This is what you would expect. You sort of lose that buoyancy there, and we get a little bit of downward displacement. Not a lot, this is millimeters, but there is an effect due to dropping the water table here. So this is the transient analysis. One thing I skipped over here is it's now possible in version 9.1 to do an implicit fluid flow. By default, it does explicit, which is what we ran before, and it ran quite quickly. So in this small, simple model, it's not really going to make any difference. But in a larger model, and especially a model where you have contrasts in permeability, this will potentially make a big difference, because if you have a very impermeable layer like some clay within more permeable material like sand, the explicit time step depends on the smallest permeability. And so it could take a very long time to reach, a very large number of steps to reach the specified time. If you do implicit, that doesn't matter. It just works out a time step intelligently to get you to the answer more quickly. You can see this actually did solve a little bit quicker, although again, it's hard to tell for this small model. And if we look at the pore pressures and the displacements, we see pretty much exactly the same thing. Okay, so that's probably the way you would do these analyses in real life in civil engineering. Something like this, where you solving fluid to some amount of time, and then solving mechanical, and solving to fluid to some amount of time, and solving mechanical. If you want to be super accurate about this, we can do what we call a coupled analysis. So I'm opening this file, slope coupled.dat. Everything down to line 10 here is the same. Now what's happening is we're doing a true coupling here. So remember with the transient analysis, we had to fudge the fluid modulus a little bit to account for the fact we were doing fluid by itself, followed by mechanical by itself, and then fluid by itself. And when we did fluid by itself, we had to adjust the fluid modulus to account for the storativity. Now we're doing a true coupled analysis, so we can just use the true modulus. And again, the true modulus of water is somewhere around 2 gigapascals. So we could just leave line 10 here, and that would be fine, and this would work. But we can speed up the analysis a little bit by, again, reducing the modulus, because this value of 2 gigapascals is very stiff. And if you're doing a soils type model, this could be hundreds or thousands of times stiffer than your mechanical material. And it doesn't really need to be that stiff. I mean, if your fluid is 1,000 times stiffer or 10,000 times stiffer, it's not going to make any difference, right? So we can reduce it a little bit, which improves our time step. And we just give this command, zone fluid modulus automatic. And what it does is it looks at the fluid stiffness that I've just specified here, and looks at the soil stiffness and says, okay, your fluid is 10,000 times stiffer than the soil. It doesn't need to be that stiff. I'll just make it 20 times stiffer than the soil, roughly, which is what it does. So you can give this command here, and all this does is speed up the analysis a little bit by reducing the modulus. Now we're doing true two-way coupling here. So we say zone fluid property pore pressure generation on. And what that means is that when the mechanical part is solving, there are volume changes, and that changes the fluid pressure. And obviously, when the fluid pressure changes, that can cause changes in the mechanical part. So if you're doing this true two-way coupling, you need this zone pore pressure generation on. 9, you don't need to do this. It's the default. In this case, we'll just start by turning on the implicit. And then now, instead of saying model solve fluid, what was the command? Model solve fluid decoupled. We say model solve fluid coupled. We give this time. And here we're specifying a little bit of a bigger solve ratio just to make it go faster. You will see when we do these true coupled analysis, it goes quite a bit slower. Well, I might as well run it while I'm speaking here. It goes quite a bit slower because what it essentially does is takes a fluid step, solves for mechanical, takes a fluid step, solves for mechanical, takes a fluid step, solves for mechanical. And each one of those solves takes a little bit of time. We can be less stringent with our solve criterion here and say, we're only going to solve to a convergence of 10 instead of 1. This will just make it go a little bit faster. Okay, that actually didn't take very long. Again, if I turn on the implicit, the fluid time steps get bigger as things start to equilibrate. And I use this convergence 10. The mechanical solve step isn't that big, or it doesn't take that long, I should say. And so this runs a bit faster. If I take out both of these parts, it will still work, of course. It'll just take longer. So we can watch this. You can see the number of mechanical steps here per fluid step as it's trying to reach mechanical equilibrium for basically every fluid step. So it does take some time. And the fluid step is relatively small here, 10 seconds or so. This is what the explicit solver calculates. When I did it implicitly, see if we can scroll back up here and find out. Yeah, the fluid time step, by the end of the implicit analysis, it actually changes as it goes along. But by the end of the fluid analysis, the implicit time step was up here around 2,000 seconds. So it definitely does make a difference. All right, this is still going. Oh, it's almost done. Oh no, fluid time is, we're still an order of magnitude too small here. So I'm just going to stop this. I can restore the save state. And we can go and have a look at it. So here's the pore pressures. Very similar to what we got with the transient analysis. You can see if I click back and forth here, I can't even see any difference. Displacement's a little bit different. Again, we see this downward displacement due to the dropping of the water table. We see a little bit more of this upward displacement here if we compare to the transient. Actually, you'll notice that the contour intervals are a little bit different. So even though this is showing red here, if I hold my mouse over, I can see that the value is about 0.0066. And if I go to the coupled, it's showing green, but again, the contour intervals are different, and the actual value is around, oh, it's still a bit lower, 0.0044. So we're getting a little bit less downward displacement, a little bit more upward displacement here. And again, this is the truly coupled analysis. It's a little bit more accurate than the transient analysis, but you know, the fact that it takes quite a bit longer means that it's generally not done in practice. You will see this used in some of the verification problems. You'll probably not see this done in real life very often. Most people do it this way, where you alternate between the fluid and the solid. And that's basically it for the fluid flow. Thank you for joining.